If you've got some cognitive dissonance around the idea of primary colors being blue, green, and red, I don't blame you. It bothered me too for a long time. But it turns out that even though red, blue, and green are the primary colors for additively mixing with light sources, when you learn about color theory from the context of most elementary school-age children learn about color, working with colored paints, the RGB system just doesn't apply. When we deal with dyes or paints or any other application of color that involves light interacting with matter, we have a completely different way of constructing color, and therefore we need a completely different set of primary colors. These colors get their name because they undergo subtractive mixing. And the primary colors are cyan, magenta, and yellow. Subtractive mixing works because matter subtracts the colors of light away from the white light by absorbing parts of the white light that are shown on it. So these are the primary colors for any kind of color that we work with our hands. Paints, technically, printer inks. Here's a picture of the ink cartridges from the second floor printer and wall as proof. Dyes, etc. all work with subtractive mixing. The primaries for subtractive colors happen to be the secondaries on the additive wheel, and vice versa. So if you're wondering where red, yellow, and blue primaries came from, it's because blue and red are close on the color wheel to cyan and magenta, and they technically fall within that broad range that we talked about in the previous video, but they also happen to be more visually appealing to younger eyes, for reasons I don't fully understand, than cyan and magenta are. So why don't you take a minute to watch the mixing for yourself, done here with lights. Fill in the results for the mixing of primary subtractive colors. Cyan and magenta make deep blue, cyan and yellow make green, magenta and yellow make red, and finally, all three together make not white, but black. Okay, so this is where subtractive comes in. Each subtractive primary appears to be its own color, or appears to be its color, because it absorbs the complementary color, effectively removing the complementary color from visible light. So we start with white light, and then we subtract away colors until we're left with black. So let's write in which color each subtractive primary absorbs. To do it, we'll have to look at the color wheel. Yellow absorbs its complement blue. I know if you look at the color wheel, you might say, no, blue-violet, but blue-violet exists in the simplified 400 to 500 nanometer range we talked about, so we're just gonna say blue. So yellow objects remove blue light. Cyan objects remove red light. And finally, magenta objects remove green. So what happens when we mix two colors together? Well, when we mix cyan and magenta, pause and predict what color you would get from removing the complement of cyan and magenta. When we mix cyan and magenta, we remove red light from the cyan and we remove green light with the magenta. That's removing 500 to 600 nanometers and then 600 to 700 nanometers. What we have left is 400 to 500 nanometers, or our blue light region. So mixing magenta and cyan together gives us a deep blue color because we subtract everything away except blue. If we mix all three together, cyan, blue, magenta, we remove blue, green, and red. If we remove all three regions of light from existence, then we're left with black. Note that if you're working with paints, it can be very hard to arrive at a perfect black. And oftentimes you end up with brown. Why? Because to do this, you have to mix each paint with equal amounts of colored molecules. And that's harder to do than you think because different paints have different strengths. So now, what happens when we mix complementary colors like blue and yellow? Take a minute and why don't you write down which color each removes or is present. Okay, so yellow light arises because we remove blue light. Subtractively, blue arises when we remove red and green light. So if we remove blue light and green light and red light, we end up with no color at all, or black. So now, we get to do the fun stuff. We get to apply these properties to dyes, or how we can use a tool called spectrophotometry to see both qualitatively and quantitatively what light a dye absorbs and how that leads to a particular color. Buckle up and stay tuned.